Okay guys, so what we're going to be talking about here is similar to what we talked about yesterday in that we're going to continue to talk about functions, but we're going to be a little bit more specific this time in what it is that we're talking about. Again, this is sort of a review. You probably have learned this somewhere along the line before, so if this looks familiar to you, don't be like, oh man, okay, this should be different, because it's really not. You've learned this kind of stuff before. And so the first thing that we are going to talk about is what certain functions look like. On the AP exam, they expect you to know what certain functions, what their behaviors are, what they appear to look like. And there's not a ton of them. There's basically 6 of them that we're going to look at. And the first of those is y equals x squared. Now the graph of y equals x squared, you've probably seen it before. It looks an awful lot like this. We call it a parabola. A parabola, again, just has a shape. It looks like a U. And so y equals x squared, when we look at it, the lowest point on the graph is at the origin, and it opens up in either direction. Now, another thing that you're expected to know on the AP exam, at least basically, is know how transformations work when we're looking at functions as well. So if I had y equals x squared plus 2, and I wanted to know what that looked like, we realize that that plus 2, what that does to a graph is it takes the entire graph and it shifts the entire graph up 2 units. Okay, so all of the y values increase by 2. So you can see some points that are already on the graph here. All of those get moved up by 2. Our graph's shape still stays basically the same. So we're still looking at a parabola, but the entire thing has been shifted up by 2 units. And again, that should sound familiar. Hopefully you've done that before. The second graph that we're going to take a look at is y equals x to the third. It actually does have a name, but we're not going to worry about it. The graph of y equals x to the third looks more like that, where it starts way down as we move from left to right. It starts at negative infinity and goes all the way up to positive infinity. This is what that graph looks like, and it is something that you need to know. If we had y equals x minus 3 to the third power, where the minus 3 is inside of the original function, then instead of moving up and down, the graph moves to the left or to the right, and it shifts the opposite of what you think it would. So this says minus 3 on the inside. That means normally you think, okay, that's going to move it to the left 3 because that's normally where negative numbers are located. But instead, we're going to move this to the right 3, and again, the graph retains its exact same shape that it had before. So it looks the same, it's just been moved to the right 3 units. This should all be reviewed. That's kind of why we're talking about it just briefly as a quick review. Y equals sine of x. Sine of x is a kind of a unique graph, and we'll talk more about that as we get further into the class. But y equals sine of x looks like this. It has what is known as a harmonic motion in that it just keeps repeating itself over and over and over. It goes up and down, up and down. If you remember, a couple of highlights about sine is it starts at 0. We do talk about radians in this class, so the graph starts repeating itself at 2 pi and is halfway through its cycle after pi units, pi x values, if you will. If I was to throw a negative in front of a function, hopefully you remember a negative just takes the graph and it reflects it across the x-axis. So instead of having what I have there, the original function, we get this upside down function, if you will, where it's been inverted like that. So y equals sine of x is the original one. I realize they're both red there, but the one I just drew would be negative sine of x because it has been reflected across the x-axis. Y equals the square root of x. That graph looks like this initially. It kind of looks like a parabola that's fallen down and lost half of itself, if you will. When we have a function like this, and in any function, we can shift it in multiple directions at the same time. So if I had y equals the square root of x minus 2 on inside of the square root, and then plus 4, the plus 4 would move that graph up 4 units, and then the minus 2, because that's inside of the function that we're talking about, would move the function to the right 2 units. And again, so we'd go right 2, up 4, so it's way up there, and then the graph retains its shape. So it would still end up looking like that square root function. Y equals e to the x is another function that appears fairly often. Y equals e to the x looks like this. Okay, it starts off very slow as we move from left to right, stays very close to the x-axis until it gets to x equals 0. Then the graph starts to grow what we call exponentially. One thing that is very important about any exponential graph, which is just a graph that has an x, and it has any variable, not just x, but any variable in the exponent, is if we take that number and raise it to the 0 power. Anything raised to the 0 power is 1. And that's actually something that's fairly important on the AP test because it shows up fairly often. And you can see that point on the graph here. 0, 1 is right there. We can see that that is included in the graph. Y equals x, the most basic of all of the functions that we have. I actually don't have a picture for this one, but that just looks like a straight line that moves up at a 45-degree angle. Okay, that one appears from time to time. We've talked about lines already in this class, so something we don't need to worry too much about. The next thing that we need to talk about are 3 things that restrict the domain of any function. The first thing when we're looking at a function is we have to realize that we can never ever divide by 0. Dividing by 0, you've learned why you can't do that before, but when we're looking at rational functions in particular, which are basically just fractions, we need to look at the bottom of the fraction so that we can know which x values it's going to be that we are going to avoid. And we'll look at a couple of examples here in just a second. So thing number 1 that we can't do is divide by 0. Thing number 2 that we can't do is we cannot take the square root of a negative number. Although they exist in more advanced levels of calculus, we only deal with real numbers here and not imaginary. So we don't look at imaginary numbers at all. If we try to take the square root of a negative number anywhere in this class, we just say that there is no solution to that particular problem. So when I'm looking at the domain, I need to make sure that I avoid taking the square root of a negative number by plugging in x values that make sure that that happens. The third thing, and we're not going to discuss this one nearly as much because it doesn't show up very often, and this is actually incorrect. That should not say negative number. That should say we cannot take the logarithm of a non-positive number. And I know those sound very similar, but we can't take the logarithm of any number unless it's positive. And if you want to know why, you'll probably have to go back and look at what you learned last year when talking about logarithms. I don't want to take the time with it right now, mostly because it doesn't happen very often, but know that that is something that we have to avoid. When we have a logarithm, we cannot take the logarithm of a non-negative number. So looking at these functions, like we've got f of x here, I don't want to solve or anything like that. I just want to know what the domain of these functions are. Well, on this first one, it's pretty easy. We say, okay, I can't have the bottom equal 0, so I want to avoid using x equals 4. X cannot equal 4 in this problem, because if I plug 4 in for x when I'm trying to evaluate, that would make the bottom equal 0, and if the bottom equals 0, then we cannot use that particular number. So I just want to avoid it in whatever it is that we're doing. That's why we find a domain restriction. Sometimes problems are a little bit more complicated where it's not readily apparent what number it is that we have to avoid. So in a problem like this, what we would have to do where the bottom is more complicated is we would need to try and factor the bottom of the function in order for us to be able to see what numbers we should avoid. So in this case, the bottom of our function factors down to x times x plus 2 times x minus 1. What that means is, technically, I want to avoid having any of those 3 different things multiplying together be 0. So I would say that x cannot equal 0, negative 2, or negative 1 in this problem. That would be the domain restriction. In other words, I just can't use those numbers. Any other number I'm totally fine using. But those 3 numbers I would have to avoid using in whatever it is that we're going to be doing with those functions. Hopefully that makes sense. When we have a square root, like we do with h of x here, what we want to do is, again, we want to avoid any negative numbers. So I would say in this case that I want x plus 4, everything that is underneath the square root, to be greater than or equal to 0. When I do that, what I would do is I would then subtract the 4, so I would say x is greater than or equal to negative 4. And so, again, when we have a square root, that's all you do. Just set it greater than or equal to 0. Okay, the next thing we need to talk about is the range. Now, the range, as you're probably well aware, the range is all of the possible y values that you can use when you're looking at a function. Most people just, when you have a graph, you just have to kind of look at the graph and understand that that's what the range is. The reason why the range is so much more difficult to find than the domain is because there are not set rules. I can't just set the bottom of something equal to 0, and I can't just take a square root and whatever is underneath the square root, set it greater than or equal to 0. So when we're looking at range, and it doesn't happen nearly as often, but just take a look at the graph and see if you can tell what the range is of the function. Like, for example, I'm not going to do all of these, I'm just going to do this first one. If I had y equals x squared plus 3, I know what that graph looks like. It is a parabola that has been shifted up 3 units. So if I was talking about the range is saying what y values exist on this graph. Well, the lowest y value is 3, and that graph goes all the way up forever and ever and ever. So we would say that our range goes starting at 3 and goes all the way to infinity. Some functions, like this x to the third plus 4, is just, again, that's that x to the third graph that's been shifted up 4 units. That graph doesn't have a lowest point or a highest point. It doesn't have a smallest value or a largest value. So anytime we don't have a smallest value, we say that the range starts at negative infinity. And anytime we don't have a specific largest value, we just call that positive infinity. And that would be the range of that particular function. Couple more things we need to talk about when it comes to functions. The next is what an even function is versus what an odd function is. An even function is a function that when we look at it, we say, okay, does that reflect across the y-axis? A parabola is a great example of an even function. Now, this is just a basic parabola. So if I had y equals x squared, that is an example of a parabola. This is an example of an even function. Notice that I can take that graph and fold it on the y-axis, and it folds on top of itself. So not all parabolas are even functions. Like if I had a parabola that existed over here, that does not fold on top of itself if I'm folding across the y-axis, which is, again, that's a big deal. An odd function is a function that when we look at it, if we take the function, or we take the entire graph, and we pick up the graph at the origin. So in other words, I kind of pick up the origin, I pinch it right there, and I turn it 180 degrees, the entire graph. Turn it 180 degrees, so flip it 180 degrees. If it looks exactly the same, then we have what is called an odd function. If it doesn't do either of those two things, then we don't have an even function or an odd function. And I know that seems kind of weird, like, okay, that seems very specific cases, but if you have even and odd functions, there are certain things that make it easier to analyze what's going on with that function. I actually think we're going to skip piecewise functions for now, other than I want you to understand a piecewise function is a function that behaves a certain way for a given amount of time, and then it behaves a different way. So like in this case, we're not going to go over drawing the entire thing, but instead, you'll notice it says y equals x for where x is between -1 and +1. We know that y equals x looks like this, but this is saying this particular function only behaves like that from x equals -1 to +1. So basically, we would avoid all of this, and we would only be interested in this graph from -1 to +1. That's the only part of the graph we would be interested in. Then from 1 to 2, the graph would behave differently. So that's what a piecewise function is. Hopefully all of those things make sense about functions. I know you've had a decent amount of training before when you've talked about functions. So hopefully all of that makes sense. And again, if you have any other questions, please come in and ask.